Hey guys, how's everyone doing?
Doing great. How about yourself?
Oh, I'm all right.
That's good to hear.
All right. We have seen. Do you guys have any questions from last time? No.
No, not particularly.
All right. We reviewed from midterm 3 last time. We did chapter 5 for like eigenvalues and eigenvectors. So we'll review. Oh no, actually, yeah, that was chapter 5. So chapter 6 we'll review today. And then we have one last section we need to do on like inner product spaces. But I think we'll finish review first, and then we'll do that section. And then like I grouped together all of the review notes for both chapters, and you should be able to find it in the module for the class for this week, like week 14, 15, like that. All right, let me switch. Okay. Yeah, you guys have one more, so you have quiz 10 still due on midterm 3 and then the final exam. So that's the only things you have left. Well, and then there's still homework. So for quizzes, I'm going to drop 3 lowest scores. All right, but then also remember that you have the online homework. So if you didn't do online homework, then kind of your homework quiz score is going to be the quiz score. But if you did do online homework and you did not do so good on the quizzes, if your homework score is higher than the quiz scores, then I'll just take that one. All right, so if you didn't do so good on the quizzes, then you can still go back and kind of finish up some of the homework problems, so you have a good grade for that. But any questions so far? No? All right, so let's finish the review, right? So we'll just do chapter 6 here, right, for the inner product spaces. So I mean, it's still pretty fresh, right? That's what the last things we did, but we can still run over it and maybe do some example problems. Right, so we did a bunch of definitions, right? We defined the inner product of two vectors, basically multiplication of the transpose of a vector by another vector, and you ending up having a scalar quantity when you do the inner product. So sometimes it's called like dot product, inner product, sometimes it's called scalar product because it's the way to multiply vectors in order to get some scalar quantity, right? You're just multiplying kind of component by component and adding everything up. And with this notion of dot product, we basically redefine some familiar quantities like length of a vector. All right, so we call it norm. All right, we have notation. So basically, length of a vector would be square root of the dot product of vector with itself. All right, and sometimes you just kind of compute the square of the norm first because so you don't use the square roots, right? You just get like v dot v. All right. And then you could also show that if I'm dotting a vector to itself, I mean, that quantity is always going to be greater than 0, or it will be equal to 0 if and only if the vector itself is 0. Just kind of by construction, if you're dotting v to itself, it's just going to be a sum of squares of its components. And I mean, squares are always going to be positive or 0, right? So in order for this to be equal to 0, each one of the components has to be equal to 0, right? So the vector has to be 0. So then we can have vectors of different lengths, but a lot of the times, like when we were dealing with like orthonormal basis and QR decomposition, right, you want to have unit vectors. So, but it's really easy to convert vectors to unit vectors. You just take a vector and divide it by its norm or by its length. Now it convert it to a unit vector, and we call it a normalization procedure, basically. And so then we did the distance between two vectors, right? The distance between two vectors was norm of the difference of those two vectors. Now, if you want to find the distance, you have a formula. And then we also defined this notion of kind of two vectors being perpendicular, except this is a more general notion. We call it orthogonal or orthogonality. We say that two vectors are orthogonal if their dot product equals to 0. So pretty kind of simple condition to check. All right. Then we also talked about, again, subspaces of a vector space V. right? If I take any subspace W of a vector space V, right, on just not V itself, because then this would be empty or just zero. All right, so we basically showed that if I take an orthogonal complement, right, W perp orthogonal complement, I mean, this is basically a set of all vectors that are orthogonal to W, right? You can write, well, I mean, my orthogonal complement is basically all vectors V in my vector space V, such that they are orthogonal to all vectors in W, right? So we're going to have W and its orthogonal complement. And we also showed that dimension of W and dimension of its orthogonal complement adds up to n, which is the dimension of a vector space V. Right? So we also did some theorems with like row space of A, null space of A. So the orthogonal complement of row space of A is the null space of A. And then kind of taking transposes, the second condition followed. But I mean, this just came from like differently writing of, if I write down the equation AX equals to 0, right, my homogeneous equation, then if I write my A in terms of its rows, right, first row, second row, nth row, when I'm doing this multiplication, I mean, each one of the components in my resulting vector is basically a dot product of the row of A and the vector X, right, because it's row by column, row by column. And when I'm multiplying it component-wise, it's equivalent to having a dot product, right? So my X being in the null space means that AX equals to 0, right? So all of those dot products equal to 0, which means that X is orthogonal to all of the rows of A. So A is orthogonal basically to row space of A, because it's all of the rows form the basis. Well, all of the rows span my row space of A. And X is orthogonal to all of the vectors that span row space. So it would be in orthogonal complement of row space of A. Right? So what it's, those theorems, but then really the most important part of the whole chapter is working with those like projections and finding orthogonal or orthonormal basis. Right? I mean, most of your homework or exam problems will be like on this stuff. Right? So kind of to summarize everything we did. Right? So we have a set of vectors. So U1 through UP. It's going to be an orthogonal set if all of those vectors are orthogonal to each other, right? So ui dot uj equals to 0 for all I not equal to j, right? I mean, ui dot ui is basically magnitude of u. So I mean, those aren't going to be equal to 0, but between any two distinct vectors in a set, they are orthogonal. And the set is orthonormal if my vectors are orthogonal and also they're all unit vectors. So the length of each one of those vectors is 1. And then we also showed that if my set of vectors is orthogonal, it automatically makes it linearly independent. So all orthogonal sets are also linearly independent. Not the other way around, but orthogonal implies linearly independent. All right. So orthogonal sets basically also generate bases for subspaces for us. So if I have an orthogonal set that spans some subspace, because they're automatically linearly independent set of p vectors, right? Taking the span of this is going to be a basis, all right, by our like basis theorem. All right, so this kind of give us, like some structure for generating bases for the subspaces. And also we found that if my basis for W is orthogonal, then it's actually really easy to compute my coordinate vectors of my vectors in that subspace, right? We don't have to do kind of row elimination algorithms like you would have to do if your vectors were just linearly independent. But for orthogonal basis to find your weights, right, for any vector y in that subspace, I mean, we have a nice little formula, right? Our weights are basically computed as like projections of my y to kind of one-dimensional subspaces generated by each one of those basis vectors, right? So we have a formula in terms of dot products to compute those weights, which is why those orthogonal bases are really, really nice and easy to use. So then we did some other theorems. So we did a theorem where we could decompose any vector in V into a sum of two vectors. So say maybe V is kind of my larger space, right? So all of this is V. And this is W, my subspace of V, with the basis U1 through UP, which is orthogonal. So if I take any vector Y in V, so it doesn't have to be in W, so it's in V, right? Then I can always decompose it into Y hat, which is orthogonal projection of Y onto W, right? So I'm just basically looking at, I mean, how does my Y look like from the point of view of just W? So basically going down at the right angle here. And the second vector that I'm adding would be the component of Y orthogonal to W, right? So technically this would be my Y minus Y hat. I mean, if you're looking at it as a triangle, you just move this vector over here, this would complete your right angle triangle. So if you don't put your vectors necessarily at the origin, you basically have Y hat plus Z equals to Y. Now, you're decomposing Y into sum of two vectors. Right? So Y is in W, and Z, because it's perpendicular to W, is going to be an orthogonal complement of W. Now, and then to do this, you basically always first compute your orthogonal projection onto W, right? So Y hat is orthogonal projection of Y onto subspace W. And here, basically what you're doing is you kind of looking at all of the basis vectors that you have for W and taking orthogonal projections onto each one of those basis vectors, right? So projecting onto U1, you have Y dot U1, U1 dot U1 times U1, right? And so on. So we have nice formulas for this. And then to get the orthogonal components, I mean, you basically just, you know Y, it's given to you. You just compute it Y hat. So you just compute Z by taking the difference between your original vector and its projection onto W. So, and then with this projection, I mean, there's different types of problems that you can do where you have to compute this orthogonal projection onto W. Like if you want to kind of approximate some vector Y and V by elements in W, right? So this orthogonal projection would be a best approximation for Y as seen from W itself, right? Or there's problems where you maybe you have to compute like what is the closest point from the vector Y to subspace W. So what is the distance from vector Y to subspace W, right? So if this is my vector Y, I mean, what is the shortest distance from Y to W? This would be basically my orthogonal component of Y in relation to W, or Y minus Y hat. And the distance between vector and subspace is basically the norm of Y minus Y hat. All right, so those are important formulas you need to know. And kind of a little bit more, right? So with my orthogonal orthonormal basis for a subspace, right? All of those vectors are orthogonal and they're all unit vectors. So if I put all of those guys in the matrix as columns, right, then we showed that multiplication of transpose by U itself, so U transpose times U would be an identity matrix. And then since my vectors are normal unit vectors, right, if I looked at my formula for the projection of Y onto W, right, and full formula we're dividing by like U1 dot U1, U2 dot U2, UP dot UP. I mean, if those are unit vectors, then all of those dot products UK dot UK are going to be equal to 1, right? So it don't really need them in a formula. And we can basically rewrite, if I wanted to rewrite this in the matrix format, I can write this as U times U transpose times Y. So just kind of different representation for the same formula, projection of Y onto W. All right. And notice that this doesn't have to be a square matrix, right? I can have UN by P, right? I have vectors in Rn, but I only have P of them. So it's not an n by n matrix. But in any case, I mean, what's nice about those orthonormal bases and when I'm forming matrices from them, this matrix will kind of preserve some important quantities. It will preserve length, right? So if I have a vector x, its magnitude, and I take the magnitude of u multiplied by x, right, where u has orthonormal columns, the length is preserved. The length is going to be the same. So multiplying by an orthonormal matrix does not change the length of the vector. And also it does not change orthogonality, or it doesn't change inner product. Like the inner product of x and y is the same as if I did ux, uy, right? And then ux, uy equals to 0 if and only if x dot y equals to 0, right? So some of those quantities are preserved with, if I'm using those orthonormal matrices. And if my orthonormal matrix consisting of orthonormal columns is a square matrix, right? To say if we're looking at vector space V and taking the basis for the entire vector space V, right? In that case, I mean, not only U transpose times U equals to identity, but the other one as well. U times U transpose is also identity. So kind of going in both directions, right? So we know that by definition of inverse, and before we showed that if inverse exists, it is unique. So, I mean, U transpose exactly satisfies condition for being an inverse. So with those matrices with orthonormal columns, it's actually really easy to do inverse. Inverse is just equals to transpose of that matrix. It's very convenient property, right? You don't have to do like row reduction algorithm on like U and I to bring it to like I and U inverse, right? You just take a transpose, it's easy. Now with all of this, since those orthonormal or orthogonal bases are so useful, how do we generate them? So for that, we have this Gram-Schmidt process to construct orthogonal bases. All right, so it constructs orthogonal bases to make them orthonormal. At the end, when you construct your orthogonal bases, you can just normalize them. So you will have an orthonormal basis. But the way it works is you basically take some basis that you have for W. So usually it is some linearly independent set, all right? And then you go kind of one by one through all of your vectors. Like you set your first vector V equals to the first vector in your original set. And then when you generate the second vector, remember you want them to be orthogonal to each other. So in order for V2 to be orthogonal to V1, I'm going to take the second vector x2 and then just subtract the component of x2 that lies along V1. So I'm only taking the part of x2 that is orthogonal to V1, so that V2 is orthogonal to V1. Right, so do x2 minus projection of x2 onto span of V1. When you've done that, you can go to the next one, take the next vector and you set x3, and then do the same thing, except now you want to only take the part of x3 that is orthogonal to both V1 and V2. So we're taking x3 and subtracting projection of x3 onto the subspace spanned by the previous two vectors, V1 and V2. And you keep going like this until the very end, right? So your very last VP would be your very last vector here, where I'm subtracting kind of the part of that vector that lies along the span of all of the previous ones, right? 1 through P minus 1. And this basically generates our orthogonal basis for the same subspace W that we had the basis for. That was my x's that were not orthogonal. All right, so it's I mean, it's a little bit time consuming because you have to do all this algebra, but it's pretty straightforward way to generate your orthogonal basis from your subspaces. Right, and you can do some examples here. So kind of something similar that can be on your test. Right, so kind of different questions could be asked, right? So I have a setup where I have basically a subspace W spanned by those two vectors, V1 and V2. Right? So they're vectors in R4, subspace spanned by two vectors, so it's two-dimensional subspace in four-dimensional space V. Right? And then I have a vector Z, right? Here, 3 minus 7, 2, 3. That's just in general R4. Like, I don't know if it's lies in W or if it's outside of W, but it's just a vector in V. So what you could be asked is, you want to maybe find the best approximation to vector Z by vectors in W, right? So, I mean, maybe I have this vector, but I'm only allowed to work with vectors in W. So I want to basically figure out how do I best approximate this vector Z if I'm only working here in W. And my best approximation would basically be the projection of Z onto the subspace W, which is just my Z hat, right? Z hat projection Z W. So we can compute this, but I noticed that you could also ask the question of what is the distance from Z to W, right? So from vector Z to W. So this would be kind of similar solution because you basically, again, need to find your projection onto W and then find the kind of length of the orthogonal component here. So we'll deal with the first part first. We're doing the best approximation. So projection, right? If I'm doing projection of Z onto W, take the basis vectors in W, and then just kind of sum up the orthogonal projections onto each one, right? The orthogonal projection of Z on V1, right? Z dot V1, V1 dot V1, V1. Z dot V2 divided by V2 dot V2, V2. This is projection on V2, right? And the sum of this basically gives me projection on the entire subspace W. And then I just, you use the formula, then I just plug it in numbers, right? So Z dot V1, I have 3 times 2 minus 7 times 1, 2 times minus 3, 3 times 1, right? So just computing your dot products. V1 dot V1 over here, dot product. This is my vector V1, right? So this is my Z dot V2. I'm just doing dot products, right? 3 times 1 minus 7 times 1, so on. This is my V2 dot V2 and V2. Now, so it's basically just algebra here, right? Compute everything, multiply 2/3 by this vector, 7/3 by this vector, and do all the algebra. So I'm getting my Z hat, right? So this vector here is going to be my orthogonal projection of Z onto W. And this is my best approximation of the vector Z if I'm only using vectors in W. So again, best approximation is just the projection. But if you wanted to find the distance from a vector to a subspace, I mean, most of our work is already done here, right? Because my distance, if this is my projection, then this vector here would be my orthogonal component, right? So an orthogonal component would be Z minus Z hat. So to compute the distance between vectors Z and W, I'm just taking the distance here, right? This would be magnitude of Z minus Z hat. Now, this is my distance. Because I already know my Z and I computed Z hat in the previous step, and easily compute the difference of those two vectors, right? This would be this vector here. So this is my basically orthogonal component. And compute kind of square of the norm of those two vectors, and then just take a square root to get the distance. So I mean, not too bad. I mean, most of those problems just basically following the formulas. Yeah. And I mean, it does help to sketch the picture sometimes. right? So you know, remember better, like exactly what you're doing, like what is the distance and you know, what is the best approximation? You know, this for me it seems like pictures help. You know, get them going. So like another type of problem you can have. So we talked about how I can always decompose my vector y in some vector space V. So if I'm given the vector and I'm given a subspace that's spanned by some other two vectors or two or more or one, right? I'm given the vector in the subspace. And I want to decompose this vector into the sum of vectors where one vector is in W and another vector is in orthogonal complement of W. Right, and you basically, again, using the same formulas we did in the previous problem, right? Vector that's in W, I need to take projection of Y onto W, right? So I'm using my V1 and V2 that span W. All right, I'm doing my projection, right? Y dot V1, V1 dot V1, Y dot V2, V2 dot V2. All right, so again, just compute your dot products. You guys are all good with that, right? And multiply them by vectors. Remember, like those guys here are just constants, they're my weights. Right? When I'm computing dot product, it's going to be this scalar over scalar, scalar over scalar. But those guys, V1 and V2 are vectors. So I'm basically writing down my projection of linear combination of the basis vectors for W here. Right, so just compute everything, simplify. Right, I'm getting that my orthogonal projection of 1 to W is this vector here, 10 over 3, 2 over 3, 8 over 3. Now, so this is going to be one vector in my sum, right, my y hat. And then to compute the second vector, because I know y, and I computed y hat. So I can compute the vector that's an orthogonal complement of W by just taking y and subtracting y hat. So that's how I'm getting my z. That makes sense? You guys have any questions so far? No? Well, good. Okay. Okay, another example here. So that one's we're going to use the Gram-Schmidt process. So, but I'm given the matrix here, right? So I have a 4x3 matrix. I can look at it as, well, it's basically 3 columns that I have in my matrix A. And so what I want to do, I want to find orthogonal basis for the column space of the matrix. So I know the column space is the span of all of the columns. Right? So I can show that, well, if I can show that they're linearly independent. But here I'm just assuming they're linearly independent already. How do I generate my orthogonal basis for the column space? Well, I have a basis of columns, A1, A2, and A3 is the basis for column space. So I can work with this basis and I can use my Gram-Schmidt to generate my orthogonal basis. And again, you start with the first one, right? You just, one vector is just one vector, right? You can just take the first column, right? 3, 1, minus 1, 3. Then when you go to generating the second one, second V, you're going to take the second column, right? And then subtract from that second column the component of that column that lies along the first one, right? You only take in the component of this column that is orthogonal to the first column, right? So I would have A2 minus projection of A2 onto V1. All right, and then again, from here, it's just applying formula, right? I have my second column, V2 dot V1, V1 dot V1. My V1 is the first column, right? So just plug everything in, compute your dot product, right? Multiply by vectors. So I'm getting this vector here, 1, 3, 3 minus 1. So, right, I got 2, V1 and V2. I mean, you can check, you multiply. If you do dot product, V1 and V2, right, I have 3, 3 minus 3 minus 3. So they are going to be orthogonal because dot product is 0. Then we still have to do one more, V3. All right, but the same way, for V3, you take in the third column and subtracting the projection of the third column onto the subspace spanned by V1 and V2. So from the third column, you only take in the component of it that's orthogonal to V1 and V2 subspace. Right, so here you just have to subtract a couple things, right? Subtracting projection of third column on V1, and you're subtracting projection of third column on V2, right? So then by construction, again, like this V3 is going to be orthogonal to both V1 and V2. But by construction, V3 is going to be an orthogonal complement of the subspace spanned by V1 and V2. Right, and here again, you just kind of compute your dot product, right, multiply by vectors, and you have your third vector. So again, we basically generated our orthogonal basis for column space of A now, right? Kind of those three vectors from my Gram-Schmidt process. That makes sense? And kind of a lot of those problems are just following. I think probably the hardest part is just like translating the problem statement, like exactly what you need to do. But the rest is just kind of using pretty much the same formulas here. So makes sense. All right, and the very last thing we did was QR factorization. So, I mean, probably, yeah, there's probably going to be like one problem on your test for this. So, I mean, we're not really, I mean, we're kind of done with all the material, but again, if you guys are doing engineering or something, if you're taking some numerical linear algebra class, like you will see this again, I guarantee you, because you use this a lot in like algorithms for solving linear systems. So we'll do that. And it's a good practice with our like orthonormal orthogonal basis. But QR factorization basically tells you that, well, okay, if I have a m by n matrix, so it doesn't have to be a square matrix, and it has linearly independent columns, right? So basically, I mean, why do I need linearly independent? Well, I need them for basically the column. If I'm looking at column space, I mean, those guys are going to be basis for the column space, right? So independent columns, I mean, those columns generate a basis for some subspace. Then I can always decompose such a matrix into multiplication of two matrices, where one matrix has columns that are orthonormal basis for column space of A. And so A's are just basis for column space, but columns of Q will be orthonormal basis for column space of A. And the other matrix is going to be square and by n. And this one would be an upper triangular invertible matrix with positive entries on the diagonal. And the way to do this, you basically just first start with looking at your columns A, converting them to orthonormal basis. So first you do Gram-Schmidt to make a orthogonal basis. Then you'll normalize it to make them unit vectors. And then to find R, you know that A equals to QR, right? And then you also know that if Q has orthonormal columns, then Q transpose times Q is the identity matrix, right? Because Q has orthonormal columns. So because of that, I can basically, I mean, instead of multiplying by Q inverse, right? Because I can't even find an inverse if Q is not a square matrix. But I can always multiply by Q transpose, and then Q transpose times Q will be identity because orthonormal columns, and R times I is R, but this gives me like a nice formula for computing R, right? You just have to take Q transpose and multiply by the original matrix A. So kind of like once you know Q, you can just use this to compute R. So that's our setup, and you can do an example here. So I have matrix A, just two columns, right? Basically, those columns are vectors in R4, right? And I want to find the QR factorization. So first step, use your Gram-Schmidt, right? For Gram-Schmidt, I'm going to only have two columns here. So I can make the first column equal to the first column in my orthogonal basis. And then the second column, to compute the second Q, I'm taking A and subtracting projection of A1 onto, or projection of A2 onto A1. So I'm just taking orthogonal component of A2, orthogonal to A1 or Q1, right? But again, here it's just formulas, right? This is my projection onto A1, compute dot product, substitute everything in, multiply, and you're getting your vector here. So with Gram-Schmidt, I'm obtaining the orthogonal basis for column space of A. But for QR factorization, I need orthonormal basis. So I mean, all I have to do to convert this to orthonormal is I'm going to take my Q1 and Q2 and divide them by their corresponding lengths, because then their magnitude would be equal to 1. Right, so if I compute length of Q1, right, 5 squared plus 1 squared plus 3 squared plus 1 squared square root, get like square root of 36. So I'm just rescaling them to make them unit vectors. So if I rescale it, yeah, I'm getting like 5 over 6, 1 over 6 minus 1/2, and so on. All right, and this is my orthonormal basis for column space of A. And this is what will go into my matrix Q. Right? So I can form my matrix Q, right? So this was my first basis vector, and this is my second basis vector. So those two columns are orthogonal, and they're also basically unit vectors. So now that I have my Q, I know that A is QR. And if I multiply by Q transpose on both sides, I'm getting that Q transpose A is R. So I can compute R by multiplying Q transpose by A. Right, so just rewrite your Q as transpose, so the rows become columns, right? 1, 6, 5, 6, column, row, column, row, column. Transpose row becomes column. I'm multiplying it by my original matrix A. No, just matrix multiplication, right? You always go row by column, right? You get this. Row by column, get second component here, right? Row by column. Row by column to get this, and row by column to get that. So gonna do arithmetic, you're getting 6, 12, 0, 6, right? So I have upper triangular matrix R with positive values and a diagonal. Basically, we did this here, right? We decomposed A into multiplication of Q and R here. So again, we're gonna do this because you guys will encounter it later in your classes. So good, like, when you see it again, that wouldn't be the first time. But as far as your exam goes, like if you do have a problem on QR factorization, like you basically would have to do this, right? Find an orthonormal basis for the column space of A, and then find R by multiplying A and Q transpose. And that's pretty much it for your chapter 6 review. So I think, if you guys just go over like the examples we did here, you should be able to be okay. But any questions? Next stuff? How do you guys feel? Yeah, and so midterm 3 will have extra credit on it also. So I posted it as it's worth 100 points, but there's actually, I think, like 110 or 115 points on it. So, and it's not like, it's not any one of the problems is extra credit, right? So you just you can do any problems. Like if you don't want to do one of them, you can skip it, but then you really should try and do all of them. Any questions, guys? Midterm? You ready?
Not so far.
All right. And, I think I don't know how many of you did quiz. Some of you did quiz 10 already. Maybe.
I'm Jabba.
I think some people did quiz 10. Yes, I'll try to grade things as soon as I can, and what I'll do is if you did the quiz and submitted it, then I'll send you the solutions for it. But I think so far I only have 5 people who did quiz 10. Because quiz 10 is on the chapter 6 problems. All right, so no questions for chapter 6. We have one last section. So this one, so we have one last section we'll do for chapter 6. So there will be problem from here on the final exam, but on the midterm, we don't have this. Like the last topic for the midterm was the QR factorization. But I mean, we should do this last section because then you probably will. I mean, if you do physics for engineering, you will see those inner product spaces. But again, those guys are not really anything. Well, it's just a more general notion of like dot product falls into a classification of an inner product, right? But the inner product is a much more general concept. And basically an inner product is something that's defined on the vector space. And it's basically a function that to each pair, like it's a function that operates on a pair of 2 vectors in the vector space. And it basically associates a real number to a pair of vectors. And for it to be an inner product, it just has to satisfy those 4 axioms. Right, so if I have any 3 vectors in the vector space V and some scalar C, the 4 properties for this function that I need to have is I want it to be commutative, right? So U in a product with V is V in a product with U, right? So my dot product did satisfy this property, right? U dot V is V dot U, so it satisfied that. And the second property, I want to be able to distribute. So if I have U plus V in a product with W, then this is the same as UW and VW, sum of inner products. Also, if you have a constant multiplied by one of the vectors in the inner product, I can always factor this constant out. And then if I'm doing inner product of a vector with itself, it's going to always be greater or equal to 0. And 0 only if the vector itself equals to 0. So for dot product that we've been using with vectors in Rn, all 4 of those conditions were satisfied. But it doesn't have to be a dot product in order to be an inner product. Basically, any definition of inner product U dot V that satisfies those 4 will be an inner product. Right, so we'll see some examples of inner products that are not dot products here. Right, but again, in Rn, our inner product, we can define it as the dot product. So we generally call it a standard inner product. Right, it's kind of like the most common one we use in Rn. And then when you have a vector space and an inner product defined on it, you'd refer to that vector space as an inner product space. Right, so you kind of have space of vectors, but you also have an operation defined on that space of vectors. And then inner product here. Right, so one example. So kind of like inner products that are not our standard inner products, right? We're still in R2. I have 2 vectors U and V in R2. And but dot products, if I was doing U dot V, this would be my U1 V1 plus U2 V2. That was the standard inner product. But I can define a different inner product. All right, so I can define inner product of U and V as not U1 V1 U2 V2, but 4 V1 U1 V1 and 5 U2 V2. But if I want to do this, I need to make sure that it is actually an inner product, right? So to show that something is an inner product, you have to basically show your 4 conditions. Is it commutative, right? Is U inner product with V equal to V inner product with U? right? I mean, you can just use your definition, right? I mean, here it's going to be commutative because I mean, if I'm switching U and V places, I mean, it will be V1, U1, right? V2, U2. And because my multiplication of scalars is commutative, then this inner product is also going to be commutative. Then you can do the same thing with distributive property, right? If I have U plus V inner product with W, just using the formula, right? U1 plus V1, W1, U2 plus V2, W2. But then again, I'm just using properties of kind of real numbers here. And yeah, I can basically split everything up and then put everything back together with definitions of my inner products. Right, so that condition holds. And that was constant also, right? Just C times U would be C U1 times 4, right, times V1. Can basically factor out C from all of this, there's C and C, and take it outside of the inner product. So third condition holds. And then the fourth condition also holds because, right, I mean, it's very similar to my original inner product because I have 4 and 5 here. U inner product with U is still going to be greater or equal to 0 because I have all positive quantities here. So like if this was -5, then I would have issues, right? Because I may end up with something negative, but I have positive numbers here. I'm good. Like it's still going to be an inner product. Right? That makes sense? Right. So it's kind of like the inner product, dot product is a special case of an inner product, but an inner product is a more general concept. Right. And we can do more examples here with inner products. So if I'm looking at the vector space of polynomials of degree at most n, right? And suppose I have some kind of n distinct real numbers, and I can evaluate polynomials at those numbers. And polynomials are defined there, right? So on that space of polynomials of degree at most n, I can define a different inner product. I'm defining it as inner product of two polynomials p and q is basically evaluating polynomials at t0, t1, all the way to tn and multiplying, right? So p of t0, q of t0, right? P of t1, q of t1, and all the way to p of tn, q of tn. Right? So I'm just plugging in whatever those fixed numbers are into polynomials and multiplying them. So that's my definition of that inner product. And to check if it is an inner product, again, you have to check all of those conditions. But I mean, I'm not going to write them out. I mean, they're pretty straightforward, right? Because I mean, I can always switch places P and Q here, right? P and Q, and then rewrite it as inner product of Q and P. All right, the same with distributive property, right? I have basically if this was P plus Q at T0, and this was K at T0, again, I'm using properties of real numbers, right? I can split this up and then regroup again. The same with constant, like if I had a constant, I can factor it out. And then for product of P with P, right? Again, I'll have right P of T0 times P of T0. So this will be P of T0 squared, P of T1 squared, P of Tn squared. I mean, this will be greater or equal to 0. And if it is equal to 0, that would mean that each one of those, P of T0, P of T1, and P of Tn, they all have to be equal to 0, right? Because they're all squares. But does that imply that P is a 0 polynomial? I mean, in general, what do we know about polynomials, right? If we have a polynomial of degree n, right, from fundamental theorem of algebra, polynomial of degree n will have at most n zeros, right? We'll have n total zeros, but distinct one will have at most n, right? So it's not going to have more than n zeros. But from over here, we see that, I mean, we're evaluating at T1 all the way to Tn. it involves have t naught. So it actually looks like we have n plus 1 zeros, right? But if polynomial has n plus 1 zeros, there's only one polynomial that can have that, and it would be a zero polynomial. So that's from fundamental theorem of algebra, if you guys remember it. All right. So, I mean, the first condition holds too, right? So P inner product with P, where inner product is defined this way, is going to be equal to 0 if and only if I have a zero polynomial. So that's also going to be an inner product, right? And can do. All right. So again, I have, I mean, something similar that we had before, but we just have some values here, right? So I have P2 polynomials of degree at most 2, right? With an inner product defined as basically taking first polynomial evaluated at 0, second polynomial evaluated at 0, right? First polynomial evaluated at 1/2, second polynomial at 1/2, and again, those two polynomials evaluated at 1. Right, so that's my formula for the inner product that I'm imposing on this vector space. Now, and if I have just some two polynomials given to me, so suppose P is 12t squared and Q is 2t minus 1, right? So, I mean, there could be any polynomials of degree at most 2. So if I want to compute my inner products, P and Q, right, you just follow the formula that you have, right? So you have P evaluated at 0. So you have 12 0 squared. You have Q evaluated at 0. So you have 2 times 0 minus 1. You have P evaluated at 1/2, right? 12 times 1/2 squared. You have Q evaluated at 1/2. So 2 times 1/2 minus 1. Right, and then P evaluated at 1 and Q evaluated at 1. Right, you get 12. That makes sense? And the same with like if I wanted to find Q dot, or not, Q inner product with Q, right? Just follow the formula. This would be Q of 0 squared, Q of 1/2 squared, Q of 1 squared. That's 2. Now, and we already showed that something in this form is going to be an inner product, right, in the previous step. Here is just n equals to 2, and we're evaluating it like 3 different points, 0, 1/2, and 1 here. That makes sense? Questions? No? All right. So a lot of other things that we did with dot products, I mean, you can do all of that with general inner products. So all those notions of like distance, length, like unit vectors, orthogonality, like all of that works for inner products also. And so we have, if we have an inner product space with an inner product defined somehow, but we know that it's an inner product because it satisfies those four conditions. Then we can kind of, with respect to that inner product, we can define same things. Length would be the square root of not v dot v, but general inner product v with v. The unit vector with respect to the inner product, right, is the vector with magnitude norm 1, right? So you just kind of define the norm in terms of the inner product. And if you want to normalize the vector, you just divide it by its norm. The distance between u and v, again, same thing as for dot product, it's just norm of u minus v. Except here your u minus v would be defined in terms of, again, inner product and not the dot product, right? You would have your square root of u minus v, right? Instead of dot product, you're using general inner product. And then the concept of orthogonality too, like you still have that for inner products, right? You have two vectors are orthogonal if and only if their inner product equals to 0. So again, dot product was just a special case of general inner products. All those things that were true for dot products will be true for general vector space, for general inner product spaces. So I can have some more examples here, right? So again, I have an inner product defined on P2, right? Where I'm just multiplying polynomials P and Q evaluated at different values of T, right? And if I want to compute the length of those vectors, right, you just basically, I mean, you can do like norm squared first, right, to avoid square roots and then take a square root later. Actually, this shouldn't be here. So just kind of plug in everything into formulas. Pretty straightforward. And then everything goes through like projections and Gram-Schmidt process. Like it was working just the same, right? So to find the orthogonal basis for finite dimensional subspaces of an inner product space, you can use Gram-Schmidt process. So we'll get to it, right? But you also have all of this like orthogonal decomposition theorem, right? If you have some orthogonal basis for W, except now you kind of orthogonality is defined in terms of the inner product here. Like orthogonal means that your UI and uj equals to 0 for I not equal to j, right? And not just the dot product, right? You can decompose any vector in your inner product space V into the sum, again, of something that's in subspace W and something that's an orthogonal complement, right? We have all the same formulas, except now instead of using dot products, we're using general inner products. Right? Instead of y dot u1, you have inner product y and u1. But everything else basically still exactly the same. You're just kind of replacing your dot products with inner products. And the Gram-Schmidt process also is pretty much the same, right? If I have a basis for W, subspace of an inner product space, I can convert that basis for W into kind of orthogonal basis for W, right? Except just here, when I'm taking projections, I'm going to use inner products instead of dot products. But it's basically, it's the same exact thing, right? Just remember that sometimes you could define those guys, inner products, like not as a dot product, but as something else, right? So if you're dealing with inner product spaces, I mean, you always have to specify how your inner product is defined, right? Because it's not always going to be the dot product. Right. But and we can practice a little bit with different inner product definitions, and kind of how to apply those theorems using kind of different dot product, different inner product definitions. So here I have P4, right? So a vector space of polynomials of degree at most 4, right? And I'm going to define my inner product of those two polynomials in P4 as basically this long string of addition, but I'm basically doing kind of evaluating P at -2 times Q at -2 plus P evaluated at -1, Q evaluated at -1, and so on. So I'm basically evaluating them at what, -2, -1, 0, 1, and 2. So kind of one other way to look at it, you're basically doing this inner product P and Q. I mean, if you're more used to just doing dot product, I mean, this would be kind of equivalent to dot product, but the dot product of the vector where I'm doing polynomial P evaluated at those 5 points, and with the vector where I have a polynomial Q evaluated at those 5 points. And when you're doing dot product, this would be P of -2 times Q of -2 plus P of -1, Q of -1. All right, so kind of another way to look at this definition, maybe a little bit easier. So, and then we have W, that is a subspace of V, and we suppose that W is all the polynomials of degree at most 2. All right, so it's a subspace of P4. So this is a 3-dimensional subspace, and this is a 5-dimensional subspace. So if you want to produce an orthogonal basis for P2 using 1t and t squared, right? This is my standard basis for P2. But I want to find an orthogonal basis, right? I can kind of use this definition of the inner product and use my Gram-Schmidt procedure to do this, right? So for the first two, so the first one, remember in Gram-Schmidt, I can take the first vector and then start generating the second vector. But here, if you notice, my first and second, 1 and t, they're already orthogonal. If I do my inner product of 1 and t, right, I'm kind of using this vector multiplication definition. So how does my 1 look like and how does my t look like? So my first vector, 1 evaluated at -2, -1, 0, 1, and 2 is still 1 everywhere. So that would be the vector for 1. For t evaluated at -2, t evaluated at -1, t evaluated at 0, t evaluated at 1 and 2, which is going to be my values t. For t squared, if I wanted to write down that vector, that would be t evaluated at -2, so -2 squared is 4. This is t evaluated at -1, -1 squared is 1. T evaluated at 0, 0 squared is 0, and then 1 squared is 1, and then 2 squared is 4. Right, so this is kind of all of the values are, my polynomial is evaluated at those different values. So to compute this inner product, one inner product with t, I'm doing vector for 1 dot vector for t, right? And here that goes to 0. So my 1 and t are already orthogonal. And since they're already orthogonal, I don't really need to do anything else. So I can kind of set my first p equal to 1, my second p equal to t. And then for my third one, t squared, I mean, you can check it's not going to be orthogonal with the other two, right? But here we can start applying our Gram-Schmidt, right? If I take my third vector t here, t squared here, what I would have to do to make an orthogonal polynomial, I have to subtract the projection of that t onto the subspace spanned by 1 and t, my two previous vectors, right? So, but again, the formula is just the same, right? I'm taking my third basis vectors in the standard basis, and I'm subtracting kind of projection onto p naught equals to 1, and I'm subtracting projection onto p1 equals to t. Except instead of dot products, I'm using those general inner products, right? So I have t squared, 1, 1, 1, right? So and then if you just compute this, right? So for this one, t squared and 1, right? This inner product would be this vector for t, 4, 1, 0, 1, 4, and a dot product with 1, 1, 1, 1, right? So it's like transpose of the first one times the second one. And then on the bottom two, I have 1 and 1, right? So this would be 1.1 vectors, right? So that's just vector multiplication, right? And then the same thing here, t squared and t, right? I am dotting this vector and this vector here, right? And divided by projection to t, so this would be my t and t inner product, right? And multiplying them by kind of my vectors p naught and p1. Right, and then simplify everything, and we're basically getting our third vector that will complete our orthogonal set. So this would be t squared minus 2. Right. Constructed basically our orthogonal basis for subspace W of all polynomials of degree at most 2. Right. So I have 1t and t squared minus 2. So if we continue using it, I mean, you basically have those corresponding vectors, like when you evaluate them to use that inner product. I'll leave that here. And remember when we did kind of best approximation with our dot products, like what's the best approximation for like some vector given I can only use vectors in W. Right, so here we can do this for functions because we're using kind of general vector spaces where it could be a vector space of functions, and we're using general inner products. Right, so if you define an inner product on a space of functions, you can use it. So if I have a vector space V of some functions, then W is the subspace of V. So my problem is I want to approximate some function f, some general function f, by a function g that's in a restricted subspace W. Right? So maybe like function f is like sine or cosine, and my W is just like the space for the polynomials. Can I approximate sine or cosine or some more complicated functions just by polynomials? And if I do, what is my best approximation with the polynomials for that function? So in the best approximation, again, here, just like with dot products and vectors in Rn, is going to be the projection of my function f onto the subspace W. All right, and this would be my best approximation function g. Now, and that the closeness of this approximation is basically going to be defined like the error in my approximation is the length of the difference of those two. If you wanted to find the error. But I mean, we can do an example. So again, we have, say, our vector space V is P4, so polynomials of degree 4. And we have an inner product defined as in the previous example. Right? So what we're doing here. Right, so we're using the same inner product. Right? And we also obtained a orthogonal basis for this inner product space, for the subspace of this inner product space. So we got this orthogonal basis from the previous example, right? 1t and t squared minus 2 subspace W. All right, so what if I have a polynomial 5 minus 1/2 t to the power 4, right? So this is the polynomial that is outside of P2, it's in P4 because it has degree 4. But if I only can use polynomials up to degree 2, can I somehow approximate this polynomial of degree 4 with a polynomial of degree 2? And how do I do this? So with our inner product here, I mean, we can use the projection to approximate this polynomial, right? So, I mean, for one, I mean, we can use that shortcut to do our dot products. So because we're evaluating at 5 points, -2, -1, 0, 1, and 2, right? So I'll write down my orthogonal basis vectors in terms of those vectors, so it's just easier to compute the, the inner product, right? And then I can also write down this vector for my polynomial P of t, right? So I have 5 1/2 t to the 4th. I'm evaluating it at -2. I'm evaluating it at -1, at 0, right, at 1, and at 2. Right, so those are just values of P evaluated at those points. Right. So then when I do my inner product, I mean, I'm just kind of doing dot products, right? So P naught and P naught would be, right, this vector dot itself. So 5, right? P1 dot P1, again, it's be 2 times 2, 1 times 1, 0, 1 times 1, 2 times 2, 10. Same with P2, right? 2 squared minus 1 squared minus 2 squared plus -1 squared plus 2 squared. And then those next what I'm doing P and P naught and P1. Again, you're just dotting stuff. So for example, P and P naught, I have 1 times -3 plus 1 times 9/2 plus 1 times 5 plus 1 times 9/2 minus 3. Right. So you basically compute this, and then your best approximation to P by polynomials in P2, right, is going to be a projection of this polynomial P in P4 onto the subspace P2, right? And you are just using the formulas, right? I have 3 orthogonal bases for P2, right? So I'm projecting P onto first one, projecting P onto second one, and projecting P onto third one, right? And again, the formula, the same, very similar to dot products. It's just instead of dot products, we're using this general inner product, right? And I computed those already here. So just plug in the values, and there you go. You have a second order polynomial, right? And this would be the best approximation to that fourth order polynomial. But in what sense is it best approximation? I mean, since our inner product is defined in terms of evaluating polynomial at those 5 points, right? 2, 1, 0, -1, and 2. I mean, your projection is basically going to be a polynomial closest to P of t in P4, but in a sense that basically it's going to be closest at those 5 points, right? Because we're using that inner product. So at the points plus -1, plus -2, and 0, right? So I have like -2, -1, 1, and 2. Right, I'm basically only checking how close the values of the polynomials are at those 5 points. All right, so they might not be so close in between, right? But I'm minimizing the error around those 5 points that are involved in computation of my inner product. Like if I was interested in other points, I could define it with other points in that inner product. Does that make sense? Yeah, any questions? Over. So I mean, like for final exam, I mean, we'll do review for final exam next time. But I mean, if you do have problems from the chapter on final exam, I mean, it's going to be something along the lines of this, right? You would be given like vector space and subspace, and the inner product is defined on it, and like I can ask you to like generate the orthonormal basis or find like the best approximation to like polynomial in P2 by polynomial in like P5 by polynomials in P3 or something like that. We'll do some more examples next time on the review for the final. Yep. All right, we have about 10 minutes and just then I plan to finish this. Yep. So there's like the last section is like there's 2 very, very useful inequalities that you can use when you deal with those inner product spaces. So we have the Cauchy-Schwarz inequality and the triangle inequality. Again, if you guys see this again, I mean, that would be kind of very, very, very useful, like very common inequalities to use. So the Cauchy-Schwarz inequality, again, we're dealing with inner product spaces, so vector spaces that are equipped with the inner product defined. But again, if I have some finite dimensional subspace W of the inner product space, and remember when we did projections, if I have a vector V that's in V, and I have a subspace W, if I take a projection of V onto W, right, so this would be this vector here, and going at the right angle. Now, if I look at it as a triangle, right, so the length of this side is projection of V onto W, length of this side is basically magnitude of or norm of V. And then this side, the length of it is basically my V minus the projection. That's my orthogonal component. So I can write this as length of V minus projection of V onto W. Now, but this is the right angle triangle. So I can basically write down my Pythagorean theorem, right? So the sum of squares of two sides equals to the hypotenuse squared. So my hypotenuse squared, sum of squares of two sides. Right? But basically another thing this tells me is that my projection of V onto W, I mean, can't really ever exceed the length of V itself. I mean, if you look at it, I mean, V here is much longer, right? Projection is always going to be either shorter, or if V lies in W, then that would be the same length. But if V is not in W, it would always be shorter because the length of this side is always going to be positive, right? Unless V is in W. So you can kind of rewrite this as an inequality that projection of V onto W length is less than or equal to V always, right? And we can use this to prove the Cauchy-Schwarz inequality, which tells us that for any two vectors u and v in the vector, the absolute value of the inner product is not going to exceed the product of lengths of the vectors u and v. So the inner product of u and v will not exceed multiplication of length of u and v. So, I mean, this could be actually very useful, especially when you get like calculus and you start defining inner products. So like the integral of kind of multiplication of two functions is also an inner product. Like if you want to show that like the integral is bounded, I mean, this comes in quite a bit. So if you guys maybe do like in differential equations, we use this a little bit. Well, at least for Palomar class, but yeah, when you go further like this, you guys will see this inequality a lot of times. But I mean, to prove this, you're basically using this result here, right? If one of the vectors is 0, then it's not interesting, right? It's going to be 0 equals to 0. But if I'm looking at non-zero vectors, u and v, right? We know that by formula for projection of v onto w, right? This would be inner product vu divided by u. Right? So my inner products are constants, right? So we know that with the norm, I can always factor out the constant out of the norm, but I have to put absolute value on it, right? That was the property of the norm. If I have c times u, then this is c multiplied by magnitude u. So I'm basically using this here. This is my c. But then what is inner product of u and u? I mean, the product of u and u is u squared, norm of u squared. So and I can even cancel out one of the norms of u because it's the squared and this is u. So what I have left is kind of absolute value of inner product of v and u divided by norm of u. But this is my projection of v onto w, and we know that projection of v onto w is less than or equal to v. So this quantity here is less than or equal to v by our Pythagorean theorem. And then from here, it just follows, right? If I multiply both sides by u, since u is not 0 and positive, inequality doesn't change. So I'm basically getting my Cauchy-Schwarz inequality. And from that one, there's the last one is the triangle inequality, which basically comes from the Cauchy-Schwarz inequality, right? So for triangle inequality tells you that for any two vectors in the vector space V, norm of the sum is less than or equal to sum of norms. All right. And you can show it pretty easily. Like if you start with the square of norm of u plus v, they write it as an inner product, then use your distributive property, right? They'll have like u dot u, u inner product u inner product v inner product u, v inner product v, right? Because commutative, your kind of mixed terms will be 2. Then right? This is norm of u squared, this is norm of v squared, this is 2u inner product with v. So inner product could be negative, but I mean, whether it's negative or positive, I mean, it will be less than or equal to if I put absolute value on u and v. Right? I mean, if it's negative, it would be less than. If it's positive, it would be equal. Right? And then from here, I know my Cauchy-Schwarz inequality, right? Absolute value of u and v is less than or equal to multiplication of norms of u and v. So I can use Cauchy-Schwarz. But then over here, it looks like I can, basically it's sum of two squares formula. So I can kind of gather it all together into one square, right? The square of the first plus twice per second plus square of the second. Now, so what I'm getting is that u plus v squared is less than or equal to norm u plus norm v. But I mean, here you have both sides are positive, right? This norm is positive, norm plus norm is positive, so I can just take square root of both sides, and I'm getting my triangle inequality, right? So, and I mean, those are our two. Again, we're not probably not going to use this much, but just for future, I mean, you guys will see those again if you're doing anything with inner products. They're super useful. And I mean, I had some more examples of. Have you guys? I don't remember. Was calculus prerequisite for this? Have you guys taken calculus? Anyone?
I've already gone through all the way through diffie Qs, so yeah.
Yeah. You guys did do calculus. Okay, I mean, I'm not gonna put calculus on the test just in case some of you didn't, but I mean, kind of another very, very common example of the inner product that you will see. I mean, you've seen this in diffie Qs, I'm sure. So, like if you have a vector space of continuous functions on some interval, you can define an inner product by basically an integral of those two functions from a to b. Inner product of f and g is multiplication of f and g, and you're integrating from a to b. You can kind of do all the same things here that we did with vectors and with polynomials, except now you're using this inner product. All right, so if you had a subspace, say my subspace is generated by 1, 2t minus 1, and 12t squared. Now, so I mean, it looks like this subspace is just P2, right? Polynomials of degree 2, right? Polynomials of degree 2, but they're also polynomials of degree 2 on interval A and B. So, but it is a subspace of continuous functions, right? Polynomials of degree 2 are continuous functions. And if you want to find an orthonormal basis, remember, you're using the same formulas, it's just your inner products are different, right? If this is a basis that you have, you can again take the first one as you had before, right? You can take the second one as you had before if it's orthogonal to the first one. So here is 1 orthogonal to 2t minus 1. Check it with an inner product. Is P1 orthogonal to P2? What is the inner product of P1 and P2? Well, if I'm using an interval AB from 0 to 1, my inner product is integral from 0 to 1 of P1 equals to 1 times P2 equals to t minus 1. So you integrate that, you get 0. Well, this one and that one are already orthogonal with respect to that inner product. So I can take my second vector to be the same as P2. And then for P3, I mean, this is not going to be orthogonal to P1 and P2. But for that, we're again using the same formulas, right? To get the third orthogonal vector, you take in the third vector here, right? And subtracting the projection of that onto the subspace spanned by the previous two. So subspace spanned by 1 and 2t minus 1. And again, you're doing it with inner products, right? You're taking your P3 projecting it onto Q1, P3 projected on Q2, and subtracting it from P3. Except now your inner products are defined in terms of integrals. So when you kind of trying to fill up, compute all of those quantities here, right? Your 12 T squared Q1, your inner product would be defined in terms of integrals. I have to compute the integral. This guy will be 4. Q1 inner product was Q1, 1 times 1, but inner product is integral from 0 to 1, 1 times 1 equals to 1. So this will be 1, right? And so on. All right, so basically you're computing other inner product, right? And then when you plug everything in to your Q3, right? So this would be your, so you're basically constructing your, okay, but you're not gonna have this on, I'm not gonna put calculus on the test because maybe some of you haven't done it yet. But just kind of to, you have a general idea. I mean, you can do a lot with inner products. Right? Any questions? Right, so far. So we basically we finished everything that we're going to do in terms of new material. So next week, finals week, right? So on Monday we will just review everything from the beginning of the semester. And then on Wednesday we'll probably just still like continue reviewing and doing some example problems. Or if some of you want to start the exam like while I'm doing the class, do that too. So yes, you can like ask questions about the exam problems. But we can talk about it more on Monday and we'll do review. Any questions? No, everyone's
No,
good.
everything makes sense. Thank you, Professor.
Okay, I'll see you guys next time.